Our second go-around at this pedestrian crossing problem is going to uh, look at two different kinds of things, one being conditional probability, but it's also going to, with a subtle change in how we approach crossing the street, really change our understanding of and use of this relative frequency and how that all is supposed to actually work. Right? So here what we're going to do to cross the street is do exactly the opposite of what our parents or guardians would like us to do, and that is, as soon as we walk up to the street, we're just going to start walking across. We're not going to look at the state of traffic and what's going on. In a sense, we will have no eyes, no ears, and no senses to vibrations. We're just going to plow right on ahead, right? And so we're asking the question, well, gee, what's the likelihood that we get across safely? Seems like it ought to go down, right? That's certainly our intuition that our likelihood of safe crossing would go down. Well, maybe in an urban setting, but not necessarily in a desert kind of setting. So, wait a minute. All right. So, how might we begin to approach that? And one of the critical aspects to doing this different kind of view or different way of thinking about it is that now that we might cross at any random point in time, not at the beginning of the gap, but at any random point in time, we need to go back and rethink what our frequencies are for these time gaps, right? And we still have the 1 to 2 to 3 to 2 to 1 ratio, but instead, since they might occur at any random point in time, it's not just a matter of reaching into the big cosmic bag and pulling out a ball that has a timestamp printed on it, but rather we got to think about what fraction of the time axis that ball occupies and where in that time axis we might actually end up. So let's take a look at taking a 3-second gap, laying it down on our time axis. We have only one of those, and we only have one 15-second, but we've proportionally scaled this interval now to be its actual length. So there's 3 and there's 15. We got two 6-second intervals and 3 9-second intervals and two 12-second intervals. So the relative frequency of just this notion of 3, 6, 9, 12, 15 are the same. However, they occupy a different fraction of the time axis, and that's a critical aspect. Right? So if we come over here and look at time occupied here for the 3-second, we just have one of those. So of course that equals a total of 3 seconds. We have 2 of the 6 seconds, that's 12, and 3 of the 9, that's 27, and then 2 times the 12 is 24, and 1 times the 15 is then, of course, 15. Add it all up, and that total is 81 seconds. So now when we go to look at the probability mass function of the time gap, in a sense, what we're sort of literally doing is we're throwing a dart down, and where does it end up on this whole time axis? Right? And so here we have a 3 out of 81 chance that the dart ends up somewhere in the 3-second gap. 12 out of 81 chance somewhere in one of the two 6-second gaps that we end up with a 6-second gap, and then 27 over 81 and 24 over 81 and 15 over 81. Obviously you could reduce those fractions if you wanted to, but I'm not going to for the purpose of making the math go adding up things later on. Right? And so the next part of taking a look at this then is to consider that our probability of safe crossing is a little bit different than before, right? That our probability of safe crossing, given that we have a time gap equal to a specific value, is going to look like the following. Probability that we have a safe crossing in 3 seconds, well, that's going to be equal to 0 because it still takes us 8 seconds to get across. Probability of safe crossing in 6 seconds, same thing, 0. Probability of safe crossing in 9 seconds is not 1 anymore, right? We have to land somewhere within the first second of that 9-second interval, or we don't make it across. Right? So that means that we have a 1/9 chance of ending up having enough time left in the 9-second gap to make it across. And that's the big difference too, as compared to how we looked at this before. When we said 9-second gap before, we were starting at the beginning of the gap, so we were assured that as soon as we started at the beginning, we'd make it across. Now we have to start within the first second. Right? And so now as we step on up the chain here, for our 12-second gap, now we have a 4/12 chance of success, right? It takes 8 seconds. And then for the last one, at 15 seconds, then we end up with a 7/15 chance of making it across safely. Right? And so when we go to now figure out exactly how to work this all out, our probability of safe crossing, still given that it takes us 8 seconds to make it across, right? So I'll go ahead and write that, 8 seconds to cross. Right, so that's a different conditional statement than what we have up here. Right? That's going to be equal to the sum of the probability that our traffic gap equals specific value, right? Or you could have made that lowercase, so that's really capital T equals T sub I, times the probability that we have safe crossing given that T is equal to T sub I. Right? So that's how this conditional probability works, and we're going to sum this over all time, and that gives us then our total probability. This total probability is broken apart into this conditional probability over here times this marginal here, the conditioning event. Right? And some of these are going to be 0. Right? So if we're summing over all time, we can just march through that. For the t equal to 3, we'd have a 3/81 chance that we're going to get t equal to 3 seconds, but we have 0 chance of making it across. Right? And likewise then, we have 12/81 chance of getting a 6-second interval, and we have 0 chance of making it across. And now we finally get some non-zero kinds of numbers here. For 9 seconds, we have 27/81 times our 1/9 chance to make it across. All right, I changed the pattern here and put this second probability inside, and plus then 24/81 times 4/12 plus 15/81 times 7/15. Why did I change? For no reason. I thought for a moment I might be able to sneak it all into the end of the line before hitting the edge of the page, and I was wrong. That wasn't going to happen. All right, so add all that up and you get 18/81, which is the exact fraction, and that's approximately 0.222, and clearly that's less than what we had before, 67%. Obviously it's safer to cross immediately after a vehicle. That's exactly what our parent or guardian would have said, right? They would also want us to look both ways and guess what the gap is going to be as well. But from just a pure probability standpoint, in this particular case, and clearly we've got the better odds if we don't go across at a random time, but we wait until a vehicle has passed, and then we go across without regard to whether we think the gap is large enough. Right now, this kind of numerical example, in conclusion, I should say, really is valid only in certain cases. Right? We can come up with a situation where this wouldn't be the case. For instance, what if there was one more possible outcome, and that is that we had a time gap that was equal to 1,000 seconds. Right? Well, on this time axis, when we laid out 1,000 seconds, it would overwhelm all this. The dart that we would throw down would be dominated by much more likely to end up in the 1,000 seconds, right? Because we only have 81 seconds here, and we throw down a dart, or excuse me, put in a 1,000-second blank, so now total is 1,081. Well, then we're going to have 1,000 divided by 1,081 chance of being in the 1,000 second gap. And then once we're there, we'd have 992 divided by 1,000, or 99.2% chance that we would blindly, randomly be able to get across safely. And that would absolutely overwhelm this whole time axis and would overwhelm the probability, and we would end up actually pathologically with the result that, hey, you're far more likely to actually get across safely if you were to just pick any random point in time, such as being out in the desert. Well, shoot, you could probably go days without any vehicles out in certain roads out in the desert, right? So there are lots of pathological examples that we could change all this, and the point really isn't to with these numbers come up with a way to cross without a signalized intersection. Rather, it's to illustrate these conditional probabilities, to take a look at this, how we can break out into total probability, this conditional probability statement here, right? Conditioning, here's the conditional probability and here's the conditioning event, and how we pull that together. You can also start to think about these as intersections and unions and that sort of thing as well. I'm going to pass on that, instead just focus on this particular representation. And in the next example, what we're going to do is we're going to take off the restriction that it takes us exactly 8 seconds to get across, and now how do we handle our probability calculation in that situation.